Okay, so we were talking about substitution reactions, of course. On Tuesday, we talked about SN1, about SN2. And so we covered about half the chapter. We're going to look at the remaining half of chapter 7 today. And we're going to continue with our discussion about substitution reactions. We were talking at the end on Tuesday about SN1, which is a substitution reaction where a nucleophile attacks, but it's first order kinetics, which means that only the electrophile affects the rate of the reaction. The nucleophile is zero order, and the electrophile is what creates that first order kinetics. And we said the reason for that is because the nucleophile is not involved in a collision in the slow step. The slow step is the loss of the leaving group. And if we want to understand these reactions in detail, we want to try to focus in on that step, because if we can facilitate the loss of the leaving group, it'll make that step happen more often. And since the nucleophile would then quickly attack afterward in a faster step, the whole process will be made to occur at a faster rate if we can facilitate the loss of the leaving group more readily. So we want to focus a little bit here on the leaving group to try to understand what makes a good leaving group, what makes a bad leaving group, and what might have to happen in some instances to turn a bad leaving group into a good leaving group. So we talked a little bit about leaving groups last time. We said the key thing about a leaving group is that it will attract electrons through an electronegativity difference with the carbon. So it won't be a good leaving group usually unless it's more electronegative than the carbon it's attached to. And in an SN2, where the nucleophile is going to attack as the leaving group's leaving, that's especially important because the leaving group will attract electrons and create a nice partial positive here, and that will attract the negative, or at least partial negative, of the nucleophile to attack. Why can't that occur in this molecule here? Well, here it's a tertiary carbon. So with 3 methyl groups and their electron clouds creating a lot of electron density here, the negative charge of the nucleophile would be repelled by those electron clouds and it wouldn't be able to attack, right? So you want to keep in mind there should be no example where a nucleophile can directly attack a tertiary carbon. It's just too crowded to do an SN2. So we know the only option here is SN1. So we're not thinking about that. What we're thinking about is, can the leaving group leave and stabilize the electrons it leaves with? And so is a negative charge going to be stable? Well, we talked about how to judge the stability of a negative charge, right? So the atom carrying the negative charge goes a long way towards stabilizing it, and oxygen isn't terrible, but it's also not very good, right? Because it's a small atom, and the charge ratio, when there's an extra negative, the ratio of negative to positive is kind of unbalanced. So as far as leaving groups go, an OH group is not such a bad leaving group that it can never leave. It's just not very stable, so a lot of times it will just come back in. And that's a situation we have here. To begin with, we have a neutral molecule with no charge, complete noble gas configurations, quite stable. If that leaving group leaves, the odds of this happening aren't very good because the leaving group will just quickly come back in and go back to the reactant side. So having the leaving group leave to create a carbocation, if the leaving group isn't very stable, it's not likely to start the process off. Right? If we're to think about the energy diagram associated with this, I don't have much space, I'll just draw a real small one. When I start with a really stable reactant that's nice and low in energy, and I'm going to form really unstable products from that first step of the process, which would be much higher in energy, well then the activation energy required to do that is going to be quite high. So kinetically, the step is not going to be likely to happen very often, and even if it does, since the reactants are much more stable than the products, it would almost always just react back anyway. It could also react forward if there was some other nucleophile around. It could also attack the carbocation there But when the OH minus leaves, at the moment it left, it's right still in the area, so it's probably pretty likely to come back in. So we want our leaving group to be as good as possible. We could try to stabilize the negative charge with the resonance. We'll see some examples of that later. But alternatively, we could focus in on the quantity of charge involved. If we didn't have to have a negative formal charge on that oxygen, it would be much more stable. And so that's why a lot of SN1 reactions will occur with a proton transfer first. So if this oxygen's lone pair picks up a proton from some kind of acid, the proton transfer would involve the OH acting as a base, picking up a proton. These electrons would stay behind on the acid, so that acid would have to be pretty strong. It would have to be pretty stable, holding the electrons behind, allowing that proton to be picked up. And if that happened, that would create a much better leaving group. So now I've created a water leaving group. We talked a little bit about this last time. We said now that it's positive, it really attracts these shared electrons much more than it would if it were just neutral. The extra positive attracts the negatively charged electrons even more. And if it were to pull them away completely, it would become quite stable. So in comparison, by protonating this, I've made it less stable, so its energy is now higher. And by now creating a set of products where one of them is neutral and stable, the products aren't so high in energy, so that allows that first step to happen much more readily, the activation energy necessary to get from a less stable, positively charged leaving group to a relatively stable, neutral leaving group after it's left. Shouldn't require much energy. So we still have a really unstable carbocation, which is why this is still higher in energy than it was to begin with. But we're facilitating that slow step by making it faster, by increasing the energy of the reactant, making it positive, and by decreasing the energy of the intermediate by making it neutral. Would that also be a helpful strategy to improve an SN2 reaction? And the answer is yes. So in an SN2 reaction, I would have to be dealing with like a primary or a secondary carbon that my leaving group's attached to. And so maybe we're dealing with a primary carbon here, so it's not too crowded. Whatever the nucleophile is, it's going to come in right away and push out the leaving group. So if I don't protonate that OH group first, I can still imagine the reaction happening where the nucleophile comes in and replaces the leaving group, but the leaving group is still unstable after it leaves. So that creates a situation where maybe this oxygen's electronegative enough to create a nice partial positive here, and that attracts the negative of the nucleophile in. A nice collision occurs there to produce these products, but if the products aren't very stable because the oxygen's still a small atom with a fairly large charge imbalance, it might come back in here and push the nucleophile out. So it would really depend on what's more stable, this nucleophile with a negative or the leaving group with a negative. So we might get some kind of equilibrium here. We might not be as product favored as we want. But if we can protonate that OH group by adding an acid first, adding an extra proton on there, now it's positive, it's really pulling these electrons away, it really is trying to leave. It can't leave first because a primary carbocation is too unstable, so don't make any primary carbocations in your mechanism. They're too unstable. Instead, the nucleophile would have to come in as the leaving group leaves, and so again it would be an SN2. And in this case, thermodynamically, once the nucleophile replaces that leaving group and the leaving group now is neutral in charge, that means that my products are actually nice and stable. So stabilizing the products helps to shift that equilibrium toward the product side and away from the reactant side. So an SN2 can also be helped with a proton transfer to make a poor leaving group into a good leaving group. And that typically is mostly used for oxygen. If I have a neutral oxygen, if it leaves, it'll be unstable. If I protonate it first and it leaves, it'll be nice and stable because it won't have any charge. So here's a complete mechanism showing that process. Again, my leaving group is not very stable. If it were to leave now and take the electrons with it, it would create a negative, so it's not very likely to do that. Almost none of the collisions that occur have the energy necessary to create both an unstable positive on a carbocation and an unstable negative on the oxygen after it leaves. So I add an acid like HCl. In this case, water would be my solvent. So I would have this happening in the background, right? We learned in Gen Chem, HCl is one of the strong acids. When HCl is dissolved in water, so this aqueous implies water is my solvent. The water picks up a proton, and I get really H3O plus and Cl minus. Right? There is no HCl molecules in water because they react with water to produce H3O plus and Cl minus. The pKa of H3O plus is around -1. The pKa of HCl is around -7. So in the equilibrium between HCl and water, it really favors the side with H3O plus existing instead of HCl existing. So it would be H3O plus actually that the OH minus would, or that the alcohol group here would react with. The lone pair would pick up a proton. Don't forget the second arrow. Every proton transfer has 2 arrows. The electrons have to stay behind. That produces a water molecule. So I produce a water here, and when this oxygen picks up a proton, I now have another water here, and this water is a great leaving group because it can be neutral. So it's going to pull these electrons away, leaving behind a carbocation, and this here is a water. It's not like it's being lost from existence or anything. It's just being formed as a side product. So a side product that's not really the focus of the reaction is often shown as something that's being lost or being produced or given away from the majority of the rest of the structure. So we're losing a water that produces a carbocation. That step is the slow step of the reaction. But since it's already relatively unstable, it doesn't require that much energy in a collision for that to leave and create a positive charge on the carbon. Then, since the Cl minus is around, as it is the conjugate base of HCl, and it's also a pretty decent nucleophile, it can come in here and attack and produce this product. Right? So that's one full mechanism for an SN1 work through and explain for you. Proton transfer steps can also occur at different stages in the mechanism. In this case, we see an example where it can occur after the substitution has happened. So let's take a look at this example. So here I have a pretty good leaving group. Cl can stabilize a negative charge much better than an oxygen because it's a much larger atom. It doesn't have nearly as much of a charge imbalance in its ratio of positive to negative charge. So here the leaving group is good. But what about the nucleophile? Well, the nucleophile is not as good. Since it's neutral and it only has a partial negative, it doesn't have the attraction to the partial positive on this carbon so much. So I definitely already know for sure that the water is not going to come in SN2 because it's too crowded at a tertiary center. So the only option for this reaction is for the chloride to leave first. If the chloride were to leave, that would create a carbocation and a Cl minus. The Cl minus is relatively stable. It might come back in, and so that step is definitely going to be reversible. Oops. But once the carbocation forms, if water's around, it can also attack. And that would produce this structure here. So now I've got a positive on my oxygen, which is also not very stable. And that's why this is not a very good nucleophile, right? Because if the nucleophile attacks and it creates something that's also a great leaving group, it might just leave. And that step might go back. Right? So if these first two steps are reversible, it's hard for me to get the equilibrium to shift toward the product side. So what I would need here to make this final product more stable would be another proton transfer, right? So it's not just a simple loss of a leaving group followed by a nucleophilic attack. We need a proton transfer at the end of the process to stabilize the product so it doesn't continue to just shift back to the reactant side. So I need another water molecule. In this case, I would need that water molecule to act as a base to pick off a proton so that these electrons can stay behind here and balance out the charge of that oxygen. So that water would then also become H3O plus. So that's a bit of a problem. It's a little bit unstable. As a fairly strong acid, the OH could pick that proton back up and that step could go back. So really, I have no especially stable reactant or product to help me recognize which side this is going to shift toward. So how can I control an equilibrium when one side isn't especially more stable than the other? Normally I know the equilibrium will shift to the side that's more stable or maybe has more entropy, but in this case it doesn't really look that stable on either side. So one way I can do that is to use Le Chatelier's principle. So in a reaction like this, another strategy that's used is to make, if I have a weak nucleophile, I would make that the solvent. If I make that the solvent, I would have lots of it around. And since it's also a reactant in this key step here, where it comes in and collides with the carbocation to produce the next intermediate, as a reactant and as the solvent, I have a huge excess of these molecules, and adding lots of a reactant helps to shift an equilibrium toward the product side, right? That's Le Chatelier's principle. If I have an equilibrium, I add a bunch of reactant, I'll facilitate the collisions, and it'll help to create more products. In order to stay at equilibrium, it will shift toward the product side when I add excess reactants. So that's a strategy there. So the water is used as a base to deprotonate. It's also used as a nucleophile. And since I'm using up more molecules of water than are forming, it's a reactant, and adding an excess of it can help shift that reaction toward the product side and give me a maximum amount of product production. So we just looked at the mechanism, and that's what we're talking about here. If the nucleophile is used as the solvent, which is called a solvolysis reaction, it's a terminology for that, it would shift the equilibrium toward products because of Le Chatelier's principle. Right? We know this is the net reaction. We also have a Cl minus. We're using two of these, and we make an H3O plus. Right? So if we're looking at the net reaction, we just showed the mechanism on the last slide. So here we're looking at the net reaction. Water is a reactant, and so if I add a whole bunch of it to the process, that will shift equilibrium toward the product side the more of it I have. And so I'm using it as a solvent for two reasons. Thermodynamically, because it's a reactant, adding excess of it will shift the equilibrium toward the product side. And kinetically, because it has to collide in the slow step, let me take that back. It's not colliding in the slow step. The slow step is the formation of the carbocation. So kinetically, adding the water is not really going to help that much because it won't really facilitate or speed up the slow step. And that's the key step we'd need to speed up to affect the reaction. So I got a little mixed up there. So really, thermodynamically is the reason we're making this a solvent, to help shift the equilibrium toward the product side. All right, anytime we're doing an SN1, that means we're going through a carbocation intermediate. We have to look out for the possibility of carbocation rearrangement. Really, anytime in any reaction where you form a carbocation, you need to look out for the possibility of carbocation rearrangement. So clearly here, the only possible leaving group is this bromine. When it leaves, it's going to create a secondary carbocation. The main thing I want to look for with the carbocation is the possibility that it could be shifted to a position where it would be stabilized by resonance. There's no way to make this carbocation allylic or stabilized by resonance though, so the best, most likely carbocation rearrangement that could occur would be a methyl hydride shift to make it go from a secondary carbon to a tertiary carbon. So I definitely don't want to move it over here. That will only make it less stable on a primary site. And so to get it over here, which is at the moment quaternary because there are 4 carbons attached, I would need to move a methyl group to that carbon, and that would be a methyl shift. So there'd still be 1 methyl group there. The other methyl group would shift over here. And now this carbon here would only have 3 bonds, so it would become the carbocation. And since it's tertiary, it's more stable than the secondary. So before the nucleophile can come in here, since this is intramolecular, it should happen before the nucleophile attacks. Any collision that the structure undergoes could align this electron cloud in this full sigma bond with the empty p orbital electron cloud, and that would quickly shift over. It wouldn't take much of an activation energy. Carbocation rearrangements have low activation energies. They're very kinetically fast, and they pretty much always happen before a nucleophile comes in, maybe with a few exceptions, but the vast majority of the molecules would undergo the carbocation rearrangement to produce a more stable carbocation before a nucleophile could attack. And so if I were looking at what the product would look like, the product would not have the nucleophile positioned here where the leaving group left. Because of the carbocation rearrangement to this site, the nucleophile would have to come in there and be connected at that tertiary carbon after it attacks at the end of the process. All right, so to kind of summarize what we just talked about, if you're trying to decide if there are proton transfers in the mechanism, look at the quality of the leaving group. If it's not a good leaving group, you might need to transfer a proton to it before it can leave, right? And so if I have an OH or an OR, right, a neutral oxygen, if it were to leave, it would create a negative charge on an oxygen. It's not a good leaving group. And so any leaving group that can't stabilize a negative, you might have to do a proton transfer first to make it positively charged so that when it leaves, it becomes neutral, and that really stabilizes it as a leaving group and facilitates the reaction kinetically. There may be, and it may be necessary to do a proton transfer at the end of the reaction. So what we're talking about there is this one over here, right? When the nucleophile attacks, since it's a weak nucleophile, it becomes positively charged. So I need a proton transfer to remove that proton and make the product stable in the end. Will the mechanism be SN1 or SN2? There are some variables that affect that, but the main 2 things that will help you answer this question in almost every instance. If I give you an electrophile and a nucleophile, and the question is, are these going to react by SN1 or are they going to react by SN2? The main thing you want to look at is how crowded is the electrophilic site. If it's a tertiary site where the leaving group is attached, it's never going to be SN2. It's too crowded for the nucleophile to come in as the leaving group's leaving. If it's a primary site that the leaving group's attached to, it's almost never going to be SN1. If it's a primary carbon that the leaving group's attached to, here, primary, but it's allylic, then it could do SN1, because if the leaving group leaves, a carbocation will be stabilized by resonance. So really it depends on the stability of the carbocation. So don't forget to look for resonance there. Don't just assume, well, just because it's primary, it'll never undergo SN1. If I don't have a carbocation, or if I don't have a pi bond here, and it's just a sigma bond, then I'm pretty much never going to have an SN1, because if the leaving group left behind a primary carbocation that's not stabilized by resonance, it would be too unstable to form in any reasonable time frame, so I wouldn't see that reaction. So looking at sterics and the stability of the carbocation will help us to understand which mechanism will occur in almost every instance. And as we saw last time, if it's a secondary carbon that the leaving group's attached to, well, that could end up doing SN1 or SN2. So there are other variables we're going to talk about here a little later to help us decide which mechanism is more reasonable or more likely to occur. And sometimes some of the molecules might react to SN1 and others might react to SN2. So we might get a mixture of mechanisms occurring for some of the molecules throughout the reaction. Is a rearrangement likely? Anytime you form a carbocation, you always want to look for any possible way to improve its stability. But remember, a carbocation shift will only occur from the very next carbon. So it's not going to be 2 or 3 carbons away where a hydride or a methyl shifts over. And it will only be a methyl or a hydride. We're not going to have a tert butyl group shifting over or anything like that, right? So there are limitations on the types of rearrangements that can occur, but you always want to look for a rearrangement to see if one can improve the stability of the carbocation. If not, then there won't be a rearrangement. And then also remember the stereochemical outcome of these mechanisms, right? So in the SN2, it has to be backside attack. So the nucleophile has to approach spatially from the opposite side of the molecule that the leaving group's leaving from. That's the only way it can occur in an SN2. And in an SN1, since you are forming a flat carbocation with an empty p orbital, once it's flat, it can never be a chiral center until the nucleophile comes in. And once it's flat and symmetrical, there will almost never be a preference for the nucleophile to come in on the top and form one spatial product or one stereochemical outcome versus connecting on the bottom, right? So almost always you'll get a racemization, or at least you'll get a mixture of different stereochemical outcomes depending on whether the nucleophile comes in from the top of that empty p orbital or from the bottom. All right, so let's look at this example here. Here we want to try to run this reaction, and so I want to convert this reactant into a product, and so I want to pay careful attention to where the carbons and hydrogens and everything are. So let me just number these carbons. It's a great way to keep track of them. So I've got a 5 carbon chain there and a 6th carbon as a methyl group that's on carbon 3. And if I do the same over here, I see the carbon skeleton is not changing. I've got 5 carbon chain and I've got a methyl group on carbon 3. What's happening though is the OH started off on carbon 4 and it's leaving. Obviously there's now a hydrogen on carbon 4 where before there was only 1 hydrogen. So drawing in the hydrogens wherever there's a change occurring is a great idea to keep track of everything. And then on carbon 3 there was a hydrogen here, but now there's none. There's this OCH3 group attached instead. So what I'm noticing here is that the nucleophile is coming into carbon 3, but the leaving group is leaving from carbon 4. So anytime I see the nucleophile attached to a different carbon that the leaving group left from, I know there's going to be a carbocation rearrangement. And based on what we said a few minutes ago, this is not a very good leaving group. So I have to facilitate it leaving. So I might add some acid. So maybe I'll just write generically H3O+. H3O+ is a good enough acid to protonate alcohols. At least some of the molecules will pick up a proton. That will make an OH2 leaving group, which will be positive, so will be much more likely to leave. Right, so let's see. I got space over here for the mechanism. So we'll go through the mechanism in a minute. So that will make my leaving group a much better leaving group. Once it leaves, I'll have a carbocation here on carbon 4, which is a secondary carbon. But then I see if carbon 3 does a hydride shift, I can get the carbocation on a tertiary carbon. And so that will happen on its own. And then I need this group to come in and attack. So what students will most often think is, well, if I add this group as a nucleophile, it'll just wait around in the reaction, and then it'll attack later when that carbocation forms. That can't do that. That's not going to work. I can't add a strong acid and a strong base and expect them not to react with one another. If I add H3O+ to try to protonate this leaving group and make it a better leaving group, and then add this methoxide, which is a strong base, and expect it to act as a nucleophile later and come into carbon-3 once the carbocation forms there, I'm overlooking the fact that these two are both in solution at the same time. They'll just react with one another. So that's not going to work. So rather than making this a strong nucleophile, I have no other option but to make it a weak nucleophile. Right, so these are my conditions. I'm going to use a little bit of acid and this methanol to act as a nucleophile. So let's take a look at the mechanism that would occur. So the first thing that would happen here is this oxygen would pick up a proton from an H3O+. That's the acid I'm using to make this a better leaving group. These electrons here would stay behind. So that would give me a structure that looks like this, where now I have a water leaving group here. That OH that was there picked up a proton. Now it's a great leaving group. I don't have a strong nucleophile. The other reactant I added was, not ethanol, but methanol. That's not a strong nucleophile. It's not really unstable. It's not likely to come through here and get through all the sterics and knock that out. This is already pretty unstable, so this would most likely collide and do a loss of a leaving group next. As we said, that would give a secondary carbocation, and then the hydride shift would help to make that more stable as a tertiary carbocation. Then the nucleophile we want to react to introduce that OCH3 group can react. It can attack there. Once that attacks at that tertiary center, it might attack from the front, giving a solid wedge. It might attack from the back, giving a dashed wedge. So if it attacks from the front, it will look like this. And this methyl group would end up getting pushed back. If it attacks, since this carbocation is flat, it could also come in from behind, which will also give me this structure. Is there a difference between these two structures? What's the relationship between them? If you're thinking they're enantiomers, you're close, but you're not correct. Because this carbon here is not a chiral center. There are two identical ethyl groups. So if I took this molecule and flipped it over like a pancake so the O methyl group, instead of sticking out at me, is now pointing behind, it looks exactly like that to this other molecule. So these two molecules are identical. They're not enantiomers. There's no chiral center. Neither is chiral. They're actually identical structures. Through rotation, I can make one exactly the same as the other, which means they're superimposable. So I don't have to draw them if they're the same structure. I did neglect something though. Once this oxygen attacks here, there's still a proton. I got to thinking about the stereochemistry there. So to complete the mechanism, I still have to pick off that proton. So that means that the water that was produced here, that it didn't draw anywhere, it can act as a base. And that water can pick this proton up to neutralize the charge of this oxygen, which would give me the product. And when the water picks that H3O+, or picks up that H+, it becomes H3O+ again, which was what we put in. So what's the term for something we start with that helps to facilitate the mechanism and then is regenerated in the end? It's acting as a catalyst. So this would be a situation where the H3O+ is my catalyst, this is my electrophile, and the methanol here is my nucleophile. So let's take a look at what the reaction coordinate diagram would look like, where we would plot the free energy versus the reaction progress. So the first step is this proton transfer. I'd be starting with H3O+ and this molecule, and they'd be this molecule is pretty stable, but the H3O+ is a little unstable, so I'm kind of starting at a relatively high energy due to the instability of this positive charge on that oxygen. Once the proton transfer occurs, now I've got the positive charge on this oxygen. That's a little bit less stable because of the sterics here. It's harder for solvation to stabilize this positive than it is to stabilize a positive on a smaller molecule that can allow more solvent molecules with a partial negative to help surround it and stabilize it. So the first step's not much difference in stability, but the first intermediate is going to be a little higher in energy or a little less stable than the H3O+. Then the leaving group leaves. The loss of the leaving group to create a secondary carbocation, that's the slow step. Carbocation formation is pretty much always a slow step. It takes a lot of energy to form a carbocation, especially a secondary one, which is not going to be very stable. The rearrangement to produce a more stable tertiary carbocation would happen quickly. That would have a low activation energy to produce a slightly more stable carbocation. Then the nucleophilic attack would help to stabilize that carbocation. Having the positive on the carbon where it doesn't have a complete noble gas configuration is less stable than the result from this attack that puts the positive on an oxygen, because at least the oxygen has a complete noble gas configuration. So that next step would release some energy. And then when the oxygen picks that proton up to regenerate H3O+, which can be more stabilized by solvation than an oxygen that's crowded by sterics, that last step would also produce a slightly more stable product. So every step of the mechanism has an activation energy and a transition state. And so you might at some point be expected to draw a reaction coordinate diagram like this, where you're at least kind of getting the general stabilities relative to one another in the right areas. So you want to look at some more examples like that to help you with that. Here's another example where proton transfers are necessary. So here I'm using H2SO4 and water to produce H3O+. Again, sulfuric acid is a strong acid. This set of conditions could have also been just used HCl and water, right? Because HCl is also a strong acid, whether it's sulfuric acid or hydrochloric acid. They're both going to put a proton onto the water to make H3O+, and that's going to start the process off with the proton transfer. And whether I'm adding Cl- ions or producing them from HCl once the proton's transferred to the water, I'm going to have Cl- ions to act as my nucleophile either way. So in this particular case, this one is going to be SN2. The reason for that is because once this OH picks up a proton to become a good leaving group, it can't leave behind a methyl carbocation. Methyl carbocation is the least stable one, and that would take a huge amount of energy to produce such a really unstable carbocation that doesn't really have any conjugation or serious induction to help stabilize it. So this would just hang out until the nucleophile collides, and it has to collide with the backside to push out the leaving group, and that would give me the product that's shown there. Again, this is not a chiral center, so it doesn't matter where I draw the chlorine in space connected to it. It's the same structure either way. So even though an SN2 normally think of as one step, sometimes a proton transfer is necessary to get the process started to make the leaving group a better leaving group so that the nucleophile can come in and push it out. If I try to imagine the nucleophile coming in here and pushing out the minus, well, that would produce a negative charge on this oxygen. That would be pretty unstable. It would just come back in and push the chlorine out, and I wouldn't get significant product. So I need the acid here kinetically to help facilitate the leaving group becoming a better leaving group, but I also need the H3O+ to make my reactants less stable so that when I look at the energy of the products, they end up being a little bit lower than the reactants, and when it reaches equilibrium, I can get a significant amount of products to form. So another example, let's see, is this an SN2 or an SN1? Well, it's going to depend on whether or not the nucleophile is attacking in the same step that the leaving group's leaving. But here I've got a three-membered ring. We talked about three-membered rings as being really unstable because of the angle strain. And they are unstable, but when oxygen is one of the three atoms in the ring, it's not nearly as unstable. We're not going to get into the reasons right now for why that is. But this functional group is called an epoxide. An epoxide is a three-membered ring where oxygen is one of the atoms making up the ring. And so this, as we said though, this three-membered ring does have angle strain and torsional strain. So opening up the ring should be something that's favored thermodynamically. But still, we don't have a great leaving group here. Even if the ring just opened up right away, it would still create a negative on an oxygen, which would be kind of unstable. So to avoid the formation of a negative formal charge, we can add H3O+. Adding H3O+ provides proton, so this oxygen can do a proton transfer. Now create a water molecule here after this electron stay as a lone pair. Now this ring is really unstable. Not only does it have the ring strain associated with the angles that are putting the electron clouds here too close, and as well as the torsional strain between the hydrogens that are eclipsing on these adjacent carbons, causing torsional strain. It also has a full formal charge on the oxygen, which is really quite unstable. So this is really susceptible to breaking open, but it can't really break open on its own because that would create a primary carbocation, which would be even more unstable. Right? There's just no instance where you're going to form a primary carbocation unless it's stabilized by resonance, but that would not be the case here. This bond can partially break though. So if I'm thinking about what's actually happening here, once this oxygen picks up a proton and becomes positive, this bond will start to break and put a significant amount of partial positive there. So it's kind of like resonance, but it's not really because it's a sigma bond rather than a pi bond shifting around. But these electrons here are not in a very stable bond. And as they start to get pulled away to stabilize the charge on the oxygen, it makes this carbon extremely susceptible to nucleophilic attack. It makes it extremely strong electrophilic site. And so that's why the water attacks there. I mean, it could attack either side because it's symmetrical, but it will attack one of those carbons and open up the ring. And that step is a very fast step. That step is very thermodynamically favorable because I open up the ring. Now I don't have any ring strain anymore. And that nucleophilic attack will occur there quite readily. But I still do have a positive charge, which is a little unstable. So another water molecule, and water would be my solvent here. Water is pretty much always assumed to be the solvent when you're working with H3O+, unless it says otherwise. So the water solvent would pick up that proton and give me ethylene glycol, which is the main component of antifreeze. It's obviously relatively stable, no formal charge or broken noble gas configurations. And so that compound can be formed by starting with an epoxide and using a substitution reaction to open up the ring with water and H3O+. Same reaction here. We want to make sure we understand the enthalpy and entropy changes that occur. So if we're looking at enthalpy and entropy, those are thermodynamic terms. We don't need to look at the mechanism. All we need to do is look at the reactants compared to the products. And we want to know which side of this equilibrium is going to be favored. Will it favor the products or the reactants? We want to look at delta G. So what are all my reactants? Well, I've got this epoxide. That's one reactant. I've got the H3O+. Is that a reactant? Well, it's starting off reacting, so it may be. But if it is regenerated in the end, it's not technically a reactant because it's not being used up. So I do have water here acting as a reactant, colliding here. In this step here, another water molecule reacts and picks up a proton. But when that picks up a proton, it regenerates the H3O+. So the H3O+ is really not a reactant. I've got the epoxide reacting, I've got this water reacting, and I've got this water reacting. So I've got three reactants. 2 molecules of water and an epoxide. And I've got products. So this is one of my products. The H3O plus is a product, but that is also reacting, so that cancels itself out. If it reacts and then is reformed later as a product, it's really canceling out in the net overall reaction. I've also formed a water here, and when this picks up a proton, that's going to make a water. So if I'm forming a water, but I'm using up two waters, the net overall effect of that is that this water that's formed will cancel one of the ones that's used. So ultimately in the overall reaction, I really have two reactants. I've got the, if I want to look at the net reaction, I've got epoxide and a water producing this ethylene glycol molecule. Oops. And I can double check that this is the net reaction by making sure that it's balanced. I have 2 carbons on this side, 2 carbons on this side, 2 oxygens on this side, 2 oxygens on this side, 4, 5, 6 hydrogens on this side, 2, 4, 6 hydrogens on the other side, so it's balanced. So this is my net reaction. If I'm interested in the thermodynamics, I'm not worried about everything else happening. The catalyst only affects the kinetics, not the thermodynamics. So to analyze enthalpy and entropy, I need to look at the reactants versus the products. So what's the enthalpy change here? Well, clearly the ring is very unstable with the angle strain and the torsional strain compared to this product over here. There's no formal charge or broken noble gas configurations. The ring strain is the only thing I can look to that makes it look unstable. So if it's unstable to begin with from an enthalpy perspective and more stable in the end, on net, delta H should be negative. What about entropy? Entropy has to do with randomness or disorder or variety. And so based on the fact that I've got 2 moles of reactants, 2 different particles, versus 1 mole of products, there should be more variety on the reactant side. Even though one is constrained to a ring and it can't rotate in a variety of ways, the water can rotate, it can vibrate, and the translational variety that it will exist here, because these 2 particles are independent and can move around independently without being connected, that's going to create usually more variety than connecting them together into one particle. So my best prediction here is that the entropy starts at a higher value and goes down, and so the entropy change is probably negative. So when this is negative, and here I've got a negative times a negative, that means I've got a negative value and I'm adding a positive value. So I don't know the sign for delta G, but I do know how I can use temperature to make the process more product favored. And that's the point here. Thermodynamics is all about trying to shift the equilibrium one way or the other. If I want to make the equilibrium produce the products, should I increase the temperature or decrease it? In this case, I want to decrease the temperature. If I decrease the temperature, this positive term will get smaller and smaller and smaller, and when I add it, it's much more likely that the negative term will be larger, making delta G negative, which means it's spontaneous or product favored. So here's an instance where I'd want the temperature to be relatively low. If I lower it too much, then I might not have the energy to get over the activation energy barrier. So I can't lower it too much, or kinetically, I won't produce enough product in a reasonable period of time. But there's going to be some optimal temperature that's low enough that favor the products thermodynamically, but high enough that I can reach the transition states and form the product in a relatively reasonable period of time kinetically. Here's another SN2 reaction. Here I've got a nucleophile attacking. I've got a nice leaving group here. My leaving group doesn't need to be protonated because I- is quite stable on its own. It's a very large atom, very minor charge imbalance when it takes on an extra electron. So that's going to produce an I-. I could say negative I- because that product being produced is quite stable. My nucleophile is weak though. So when it attacks, clearly it's a primary carbon. The leaving group can't leave first. It can't leave behind an unstable primary carbocation. So the attack would have to happen as the leaving group leaves. So it's definitely an example of an SN2. But since the nucleophile is relatively weak, Once it attacks, it's going to be positive. And so I would need another molecule of the nucleophile, and I would make this my solvent. So there'd be lots of it around, and it could easily collide here and pick that proton up and produce a product. Once it picks up the proton, though, it would exist with a positive charge itself. So if I want to look at the thermodynamics here, what about the enthalpy? Well, if I'm going to look at thermodynamics, I want the net overall reaction. So what are my reactants? Well, I've got this initial reactant with the iodine. That's one of my reactants. What else? I've got an ethanol here that's reacting. I've got another ethanol here that's reacting. So there are two of those that react. And what are my products? I'm producing this ether. And I'm producing this thing here, a protonated ethanol with a positive charge. And the I- is a product. So counting up your products and reactants, you got to be real careful about that. You got to make sure everything's balanced in the end. You got equal numbers of carbons and everything on both sides. Then you can look at enthalpy and entropy. So from an enthalpy standpoint, which side looks more stable? Well, the I- is quite stable, this ether is stable, but this positive charge over here, not very stable. So this is a situation where delta H probably is positive. Having the unstable formal charge on the oxygen, even though the charge on the iodine is quite stable, probably not, it's probably higher potential energy or less stable than the reactant side. So let's take a look at entropy. Entropy mostly focuses on the number of moles. So I have 1 mole of this reactant and 2 moles of ethanol, so that's 3 total moles. And I've got 3 things formed in the end, so that's 3 total moles. So it's really hard to say which side will have more variety when I have equal amounts of particles on both sides. So the entropy is probably relatively close to 0. And so if I'm looking at the free energy and the entropy term is close to 0, well, then the equation can be reduced to the free energy depending on delta H. And so this is a process that's probably not going to be very product favored. If I want to shift it to the product side in the equilibrium, I need some other strategy. And so that is why I would use the ethanol as a solvent. Adding a large excess of the ethanol should help, by the Chatelier's principle, shift it to the opposite side. And using it as a solvent should provide plenty of excess. And so that's probably my best bet at shifting that substitution reaction toward the product side. Are carbocation rearrangements possible here? And the answer is no. There's no carbocation formed, so there's no way that a carbocation could rearrange if it doesn't even form to begin with. All right, so we've talked about a variety of these factors, but if we're in a situation where we have to decide if the reaction is going to happen by an SN1 mechanism or whether it's going to happen by an SN2 mechanism, we want to carefully analyze each of these factors before we really make the determination. So in some instances, it'll be obvious, but it won't always be. So let's go through these one by one. And some we've already talked about, but the possibility of an SN1 requires that we form a carbocation. So whether or not that can occur will depend a lot on the stability of the carbocation that's created. And there's a couple types of carbocations that we haven't really seen yet, so we want to look at them in detail. And that requires a couple new terms to be introduced. So if you recall, a vinyl carbocation would be one where the carbocation is right on the double bond. And that is very unstable because it's an empty sp2 orbital, which is a compact orbital close to the nucleus, and that's really unstable to create a vacant space next to the nucleus because the nucleus will very quickly attract electrons into that space. So that's quite unstable. So we want to recognize that if a leaving group is vinyl, it is not going to leave behind a vinyl carbocation. too unstable, these electrons are too close to the nucleus in an sp2 orbital to just be pulled away from that carbon by a leaving group. Conversely, though, an allylic leaving group can leave pretty readily, because if an allylic leaving group leaves, I get an allylic carbocation. Even though if it's primary, it doesn't matter because it's stabilized by resonance, and the positive charge spread out over two different carbons allows that leaving group to leave behind a relatively stable carbocation. So there's a big difference between the stability of a vinyl carbocation and an allyl carbocation. These two terms are very similar. The aryl is similar to the vinyl. Aryl means that you have an aromatic or benzene ring. So an aryl group is one that's directly on the ring. So if I put a leaving group here, it really can't leave. Just like the leaving group can't leave from a vinyl carbon, it can't leave from an aryl carbon. Because if it were, I would get a carbocation right on the ring. And again, that's an sp2 orbital, and so it's really not possible for the leaving group to pull electrons away from an sp2 hybridized carbon when they're really close to the nucleus in a tightly compacted sp2 orbital. So we're not going to get that, just like we're not going to get this. Right? So make sure you understand, don't do an SN1 on a vinyl or aryl leaving group. Benzyl is a little bit different. Benzyl is where the leaving group isn't directly on the ring, but it's one carbon away. So now the leaving group can leave, because if it leaves, it'll create a carbocation that's stabilized through resonance. So even if it's primary, doesn't matter. The electrons from the ring can swing out, and these can swing over, and these can swing down. So that positive charge would actually be distributed over 4 total carbons, including the original location. So that would be nice and stable through resonance. I mean, it's not super stable, it's still unstable carbocation, but relative to other carbocations, pretty stable way to spread out positive charges. So it's easy for an allyl or a benzyl leaving group to leave and go through an SN1 mechanism, but impossible from a kinetic standpoint for a leaving group to leave from a vinyl or an aryl carbon. So we did say when we have an allylic or benzylic leaving group that can leave, that would create a carbocation on a carbon that's allylic or benzylic, and it would be stabilized through resonance. So we talked about that. So we know that if the carbocation that forms is relatively stable compared to other carbocations, the SN1 mechanism is definitely a possibility that we would want to consider. And so those molecules can readily undergo SN1, and here's how the resonance structures would look for those, and why the carbocation that would form there would be relatively stable. Are they more likely to undergo SN1 or SN2? Well, they're pretty good at going through SN1, and what's the main factor that determines SN2? That would be sterics. So in these particular examples, since these two carbons that the leaving group's leaving from are primary carbons, these can undergo SN1, where the leaving group will leave first, creating a carbocation, and then the nucleophile could come in and attack that carbocation at either one of these carbons, actually. But it's also possible that the nucleophile could come in directly. Because it's a primary carbon, it's not too crowded. The nucleophile, depending on how crowded the nucleophile is, if it's one atom or a couple atoms, it could probably make its way in there. If it's a whole bunch of atoms with a big electron cloud, it might not make it in. It'd be more likely for it to do SN1. So sterics is the main thing that you want to look at when you're trying to determine whether an SN2 mechanism is going to occur. As we said, do not make vinyl or aryl carbocations. Those molecules don't go through SN1, and they also don't go through SN2. So even if I have a leaving group on either one of these carbons, it really can't leave. Because of sterics, I can't do SN2. Right? That SN2 requires a backside attack. It requires the nucleophile to come in exactly 180 degrees away from where the leaving group is. But if this is an sp2 hybridized carbon, it's flat. And this ring is in that plane. And the nucleophile, there's no way it's going to make it in there. It doesn't have to be tertiary carbon to block out the nucleophile. If it's flat and the ring is in the exact same plane that the nucleophile would have to attack through, there's no way sterics blocks that. So we can't do an SN2 there. We're really even here, even though it's just a hydrogen, this cloud of electrons and neutrons, they're in the plane that the nucleophile would have to attack through to get to the backside of the leaving group. So we're not going to see that happening. So we can't do an SN2 on a vinyl or aryl leaving group because of the rest of the molecule being in the plane where attack would be necessary, blocking it out through sterics. And we can't do an SN1 either because if the leaving group were to try to leave first, the carbocation that would result would be really unstable. The leaving group, even if the leaving group is stable with a negative, it can't pull the electrons away from an sp2 orbital because that orbital is compact and the electrons are too tightly held to the carbon's nucleus. They're not going to be ripped away even if the leaving group is very electronegative and even if it can be stable with the electrons on its own. So there are a couple situations where you won't see substitution occurring even if you do have a leaving group. Alright, so let's take a look at the next factor, which is the quality of the nucleophile. And we talked about this a little bit when we were talking about SN2. We said if it's going to be SN2, what that means is whatever carbon the leaving group's attached to, the nucleophile has to attack as the leaving group's leaving. We said sterics is a big issue there, but also the strength of the nucleophile is a big issue. If the nucleophile is really unstable, then it's already starting relatively high in energy. During the collision, there might be some sterics. There are definitely some bonds breaking and forming, which is unstable. So during the collision, it's going to be pretty high in energy. But if the nucleophile is already unstable and it's already starting pretty high in energy, then the collision necessary to get to the transition state, most of the collisions might have the energy necessary to do it, so it's reasonable to propose an SN2 mechanism there. If I start with a nucleophile that's maybe neutral or really stable, and it's already lower in energy to begin with, well then to get to the transition state requires a lot more energy. So it's less likely to go through an SN2 if the nucleophile is stable because the activation energy necessary to get to the SN2 transition state where the nucleophile attacks and the leaving group leaves at the same time requires a lot of energy. It's just not going to happen very often. So kinetically, the stronger the nucleophile, the more likely it is to react. So what makes a nucleophile strong or weak? What makes it unstable? Well,
wait, so
yes, go ahead.
Stronger nucleophile would go through SN2 probably, and a more neutral one would be SN1?
Yes. Obviously, there are other factors at play as well. So it's not just like a black and white, strong always does SN2 and weak always does SN1. We have to also look at sterics and the stability of the carbocation. But this is just one more factor that plays in that you might want to, that you might be asked about, and you might need to talk about and explain a little bit in an exam answer. But yeah, what you said is correct generally. So if the nucleophile is stable, maybe there's induction. So I could have, maybe if I have an oxygen that's negatively charged, that's probably a pretty good nucleophile. But if there's a bunch of fluorine atoms here, that makes it a weaker nucleophile because the fluorine atoms attract electrons and that pulls these electrons over, and so there isn't as much negative charge around the oxygen, right? So the factors that affect the stability of negative charge that we've already talked about are the same factors here. If the negative charge is stabilized by induction, or if it's stabilized through resonance, it's not going to be as concentrated on one area, it's not going to be as unstable or reactive, and so it's not as likely to start the ball rolling by attacking as the leaving group's leaving. It's less likely to do an SN2. Solvation is a big factor as well. If the solvent is able to really surround this nucleophile and attract to it, form really strong attraction, well then the nucleophile really can't attack the electrophile and push out the leaving group because the solvent is in the way. So we're going to see some examples of that and how solvent selection can affect whether it's SN1 or SN2. And then sterics is a huge factor, as we've been saying. Not just the sterics of the electrophile, which is what we've been mostly focusing on. We said, like, if the leaving group is attached to a primary carbon, usually SN2 can happen pretty readily. But if my nucleophile has a huge cloud of electrons, like maybe it's an oxygen with like a terp butyl group or something, and this cloud of electrons is really big, it might not be very easy for the nucleophile to make it all the way in there and push out the leaving group. So in that case, an SN2 might be less of an option. In that case, an SN1 is also not an option though, right? Because leaving behind a primary carbocation that's not stabilized by resonance is prohibitively unstable as well. So that might get into a situation where we'd have to look at a different mechanism, something that's different from SN1 and also different from SN2, which we're going to talk about in Chapter 8. So we want to get you thinking about the concepts that are important, right? So the more unstable the nucleophile is, the more likely it'll be to react right away in an SN2, and the less sterically hindered the nucleophile is, the more likely it is to get right in there and collide as the leaving group's leaving as well to do an SN2. So will a strong nucleophile favor SN1 or SN2? It'll favor SN2. It'll be more likely to collide right away and push out the leaving group. And a strong nucleophile is one that's not stable. It's not stabilized by any of these factors that stabilize a negative charge. Any questions about any of that? All right, so the quality of the leaving group is obviously important, especially for SN1, because in an SN1, the leaving group has to leave first. So if I'm talking about a bad leaving group, one that can't stabilize the electrons it leaves with, it's not very likely to do an SN1, right? Because in an SN1, when the leaving group leaves, it's going to leave behind a carbocation, which is already pretty unstable. If when the leaving group leaves, it also can't stabilize the electrons it has because maybe it's a negative charge and there's not really good solvation or induction, or the atom carrying the charge can't stabilize it, maybe there's no resonance to stabilize it. So all of the stereo factors we talked about to stabilize a negative, if they're not at play stabilizing this negative charge well, it'll probably just come back in. So it's hard to get a leaving group to leave and facilitate an SN1 mechanism and leave behind a really unstable carbocation if it's not a good leaving group. Really, we need a good leaving group for both of these mechanisms. If there is not a leaving group that's decent at all, no substitution is going to occur. But we definitely need a good leaving group if we expect an SN1 to occur, because, as we said, that leaving group leaving is the slow step. And if we want an SN1 to happen, we need to facilitate the slow step as much as possible by stabilizing the leaving group and the carbocation both as much as possible. So what are some good and bad leaving groups? Well, put this in here so you can check out the figure in the textbook that shows some of the good and the bad leaving groups. If we look at that page specifically in the textbook, that is on page 323 and 324. What we see is a neutral leaving group is going to be nice and strong. A negative charge on a halogen. So the good leaving groups, neutral ones like water, halides, Br-, Cl-, I- are all great leaving groups. And as we saw last time, some of them might have resonance. So if the leaving group has a negative on an oxygen, that's not a very good leaving group. But if it can be stabilized on multiple oxygens through resonance, that makes a much better leaving group. So those are your best leaving groups. If you see any of these leaving groups, especially one with a positive or any of these really stable negatives, that's definitely a good sign that those are going to be leaving from the carbon, either by an SN1 to create a carbocation, or if it's not too sterically hindered, maybe the nucleophile would come in right away and push them out in one step. So what's happening here in this reaction? Well, I'm just showing you, here's an example of a really terrible leaving group. Right? So stabilizing a negative charge works well on these halides and on an oxygen that's stabilized through resonance, but not on a hydrogen. Right? So this molecule is not going to undergo a substitution. No matter how strong my nucleophile is, it's not going to come in here and push out a hydrogen. A hydrogen leaving with a pair of electrons would be really unstable with a negative, right? Because it would have two negatives and only one positive proton in its nucleus. So when I have twice as much negative as positive, that's really, really very unstable. So I don't really ever expect to see a hydrogen as a leaving group. I don't really ever expect to see a carbon as a leaving group. If a nucleophile attacked here and this carbon group left, then the carbon would have a negative charge. So a leaving group is not going to be one that's really unstable, like a hydrogen or a carbon with a negative charge. So just watch out for that as well. So here are some of the most stable leaving groups. This tosylate one we're going to see on a lot of examples this semester and as well next semester. This oxygen carrying a negative that can be stabilized through resonance with the other oxygen atoms really helps to stabilize a negative charge. And I think, I'm not sure, maybe because it's relatively cheap, this can be installed on molecules as a leaving group and replaced with a variety of different nucleophiles. So it's synthetically useful and a relatively common one that the textbook focuses on. But there are also other sulfonate leaving groups, and the halide leaving groups are also really common. So we see lots of examples where those are involved. All right, so we're going to talk a little bit about the nucleophile. As we already said, the stronger the nucleophile, the more likely it is to get involved right away and push out the leaving group in one step. It may go by SN1 though, if it's too sterically hindered, right? So we already talked about SN2 cannot happen on a tertiary carbon. It's just too sterically hindered for the nucleophile to attack, no matter how strong it is. If the leaving group's attached to a tertiary carbon, it's going to be too crowded. But typically, if I have one of these strong nucleophiles, so a negative charge on a halogen, or on a sulfur, or an oxygen, and especially on a carbon, very strong nucleophile, carbon really needs to share those electrons to balance out its charge. Sulfur happens to be a great element to be nucleophilic. So, in general, what we've been saying about bases and negative charges is that if the atom carrying a negative charge is a larger atom, it's usually more stable with a negative charge. But larger atoms form relatively strong sigma bonds, so they do make pretty good nucleophiles. So when you're dealing with a sulfur, whether it's negative or neutral, it's pretty good at sharing its electrons with carbon. And the same for the halogens. So those are pretty common nucleophiles, and you can expect them to come in and push out a leaving group in a variety of different reactions, whether it be SN2 pushing out the leaving group in one step, or maybe the leaving group is too sterically hindered, so it has to leave behind a carbocation, and then one of these nucleophiles attacks. But you want to be at least roughly familiar with the halides, with sulfur, with an oxygen that's negative, and carbon that's negative. Those are the main nucleophiles that you'll see in almost every example that we look at. The neutral oxygens are nucleophiles, but they're much weaker, and at least in protic solvents, which we'll talk more about in a minute, a fluoride is not a very good leaving group because it's so small and its negative is so concentrated. It really attracts in, especially in like a solvent like water, it really attracts strongly these partial positives of the solvent. If the solvent has a really exposed partial positive on a hydrogen because the solvent's capable of forming hydrogen bonds, these hydrogen bonds are really strong. So a fluoride will get surrounded by water molecules, and that makes it really hard for it to act as a nucleophile because the water molecules are kind of in its way, blocking it from attacking an electrophilic site. And then obviously the neutral ones aren't very good nucleophiles because if they attack, then they start to carry a positive formal charge, and then they often just fall back off or act as leaving groups after that. So they're not as likely to attack if they're already stable. So the unstable ones with the negative charge, or the sulfurs that can form nice strong sigma bonds, are your best nucleophiles in most situations. So we talked about that pretty thoroughly. All right, so now I want to talk about the solvent and how the solvent can affect or facilitate substitutions in general, as well as SN1 versus SN2. So, or in other words, how can I use a solvent to help me control which mechanism is more likely to occur? So we know the solvent helps to facilitate a reaction. The main way it does that is by forming attractions to the transition state. And so we're going to see here in the next few slides how that works. Right? So the solvent surrounds each molecule, it helps them collide, and it really helps to stabilize the structures during the collision. And that's really important kinetically. Right? So here are your transition states for an SN1 and your transition state for an SN2. Right? In an SN1, we're looking at the slow step here, right? This is the step. If we could speed up the loss of the leaving group, we'd speed up the overall process, because that's the bottleneck of the process. That's what's slowing everything down. So whatever my solvent is, I want it to be polar. I want to have a polar solvent, one that has a partial positive end and a partial negative end, so that the solvent can form some nice attractions here and stabilize these transition states. The transition states involve partial charges, right? If the leaving group's leaving, it's pulling the electrons away. It starts to take on a negative as it pulls the electrons away. It's not fully gone yet, and these electrons are really unstable because they're not in a proper orbital during the collision and the bond breaking or forming process. But as they slowly get pulled away, or as they start to get pulled away, and I start to form these partial charges, the better the attractions between the solvent and these charges, the more stable the transition state will be. So if I try to imagine this first step in an SN1 where the leaving group leaves, this is the reactant. If I had no solvent at all, the transition state would be extremely unstable. All right, solventless transition state. If I don't have solvent around to form any attractions here, then when these partial charges form, it's going to be really unstable. And kinetically, this reaction is almost never going to occur. So if I want this reaction to be successful kinetically and actually get to the transition state, I need the transition state to be low enough that most of the collisions will have the energy necessary to get there. And the solvent plays a huge role in that. I need the solvent to be polar so that it can form attractions during the transition state, and the transition state can be low enough where a lot of the collisions will get to the transition state. And that's true for the SN1 and for the SN2, because in both mechanisms, whatever transition state I'm looking at, there are partial charges on the structure that forms during the transition state, and if the solvent can form attractions, that helps to stabilize that structure and make it lower in energy than it would be without the solvent. So I need the solvent to stabilize the transition state for both of these mechanisms for them to work. And the solvent needs to be polar in order to stabilize it, right? If the solvent were nonpolar, and it's just a nonpolar structure, it didn't have opposite charges on opposite ends, it really would only be able to form London force attractions here, which is a much weaker attraction, and without very strong attractions, it's going to be very high in energy. It wouldn't be as high as it would be with no solvent. It would still be lower, with a nonpolar solvent, but it would be much higher with a nonpolar solvent than with a polar solvent, because a polar solvent stabilizes the transition state, makes it lower in energy by forming attractions to it. So in an SN2 though, not only do we want to stabilize the transition state, we also need to facilitate collisions between the nucleophile and the electrophile, right? In the SN2 reaction, they have to collide together because the nucleophile has to come in from the backside and push out the leaving group in one step. So what type of solvent would I use? Well, I need a polar solvent because what we just showed on the last slide. If I don't have a polar solvent, I can't stabilize the transition state well, and the whole thing will almost never happen because very few of the collisions will have the energy necessary to get to a really high energy transition state. But if it's too polar, then as we said, it might surround the nucleophile too strongly. And if all these partial positive ends of my solvent come in and surround the nucleophile and really stabilize it, it can't really break free from that solvent shell and come in and attack. So I'm hindering the SN2 if my solvent has too much of a partial positive that attracts too strongly to the nucleophile. And so if we look at a couple examples of some solvents, we can see this playing out. So here's an example reaction that would have to be an SN2 because it's a primary carbon. I can't have the leaving group leave first and leave behind an unstable primary carbocation that's not stabilized by resonance or anything. So the negative charge on my nucleophile, it would have to come in and push out the leaving group in one step. There's no way around that. And so we can experimentally look at some different solvents and look at the reaction rate. When I use methanol or water, the reaction rate is relatively slow. When I use some of these other solvents, the reaction rate is thousands of times faster. And so what's the difference? Well, let's take a look at some of the structures of these solvents to see if we can understand. So the solvents here that are the fastest are called polar aprotic. They're not protic solvents. And if we look at their structures like DMSO and acetonitrile, looking at their structures, what do we see? Well, they're definitely polar because their electronegativity difference here is going to create a negative end and a positive end. Same thing here, the nitrogen is significantly more electronegative than carbon. When all three electron pairs shift in that direction, I'm getting pretty decent opposite charges on opposite ends of the structure. And the negative part of that is exposed and pretty highly concentrated with negative, so it can form some pretty nice attractions to the counterion of the nucleophile. We don't usually think about the counterion, but it's pretty important because if I can't attract this counterion to let my nucleophile free, well then the nucleophile will be stuck forming attractions with the counterion. This is a delicate process. I've got to get the nucleophile away from the counterion, and I've got to make sure the nucleophile doesn't get too well solvated so that it's free to attack the electrophile. So I want a solvent that's polar aprotic. The polar aprotic solvent like DMSO or acetonitrile or acetone or DMF. Each of these solvents has a nice area of partial negative that's nice and exposed, that can surround the counterion and allow the nucleophile to get free from the counterion. And the fact that they are aprotic means that they don't have any hydrogens that are carrying an especially large partial positive. Where's the partial positive on each one of these? It's on the carbon, or the sulfur, or the carbon, or the carbon. And when carbon or sulfur carry a partial positive and they're surrounded by other groups that create a little steric hindrance, it's really hard for the partial positive of any one of these solvents to surround the nucleophile. Right? In order for this solvent to form a nice attraction to the nucleophile, it would have to come down in here and get this carbon next to the chloride. But this methyl group's kind of blocking it out a little bit. You know, if I brought the DMSO in there, I'd have to get sulfur kind of close here, but these methyl groups are blocking it out a little bit. It's not like water, where the large partial positive is very exposed and can easily form a really nice attraction there and surround the nucleophile. So with a polar aprotic solvent, the solvent can surround the counter ion, the sodium. It has a nice polarity to stabilize the transition state when it forms, but it doesn't have a really large partial positive on an exposed area, so it can not very effectively stabilize the nucleophile. So it's really the best of both worlds. It stabilizes the transition state pretty well, but it doesn't stabilize the reactant too well. And so we end up with a situation like this. If I'm doing an SN2 and I have a nucleophile that I want to attack and push out a leaving group, if I use a polar protic solvent, the polar protic solvent, protic means it's capable of hydrogen bonding, so that would be something like water. If I use a polar protic solvent, the water molecules surround the nucleophile and form really nice attractions to it, and that stabilizes it. So yes, the transition state is also stabilized, but if the reactant is too stable, well, most of the collisions won't have the energy necessary to get up there, and it slows down the process. And very few products, molecules will be formed in a given period of time if there's a very high activation energy. So we don't want a polar protic solvent when we're doing an SN2. If we want the nucleophile to attack right away, we want the nucleophile free. We want it naked. We don't want it surrounded by solvent molecules that will prevent it from attacking. So a polar aprotic solvent doesn't form very strong attractions to the nucleophile. It can't hydrogen bond to the nucleophile. It can only form weaker dipole-dipoles that are somewhat blocked by these methyl groups that are often crowding it out a little bit on either side of the atom that carries the most partial positive. So with the polar aprotic solvent, it doesn't stabilize the nucleophile very well, but it does stabilize the transition state pretty decently, because as we said, during the transition state, it doesn't have to be protic or aprotic. As long as it's polar, it can stabilize these transition states. So the transition state energy will be relatively low, and the reactant energy will be relatively high. So this red line here indicates a reaction that's really nicely facilitated by the solvent. It won't take much activation energy. Lots of products will be formed in a relatively short period of time because the activation energy is much lower when the reactant isn't so stabilized by the solvent. If I want to promote an SN1, I don't care about how the solvent stabilizes a nucleophile, because the nucleophile is not even involved in the slow step. If I want to promote an SN1, my only concern is to stabilize the transition state in the slow step. And so how do I do that? Well, the transition state, as we said, in the slow step for an SN1 is going to be when the leaving group starts to leave and pull electrons away from probably a secondary or tertiary carbocation. So in that case, I need a solvent that has a nice large partial negative and a nice large partial positive. The partial negative can come in here and attract to the partial positive that forms where the carbocation will end up. And the protic site on the solvent that's carrying a large partial positive, because it's capable of hydrogen bonding since it's bonded to a highly electronegative oxygen or nitrogen, that highly electronegative atom creates a large partial positive there. So the partial positive can then come in and form a nice attraction to the leaving group to facilitate the loss of the leaving group. And those protic solvents will also form a strong attraction to the nucleophile, but I don't care about that because that's not part of the slow step. I only care about speeding up the slow step if I want to facilitate an SN1. If I want to facilitate an SN1, I want to use a solvent that's as polar as possible to form the strongest attractions during the slow step that can form. And that way, the slow step will happen a lot more often because we'll go through a much lower energy transition state. And since the nucleophile is not involved until the second step, even if the second step was, a little higher, it doesn't matter. It's never going to be higher than the first step, and so it really is irrelevant in the kinetic analysis. What matters is speeding up the slow step, and so I want to speed up this step by stabilizing the loss of the leaving group and the partial charges that form there during the transition state of that loss of leaving group step. Any questions about any of that? All right. So we'll also talk about some of these halide nucleophiles a little bit because there is a solvent effect on their stability or reactivity as a nucleophile. So we were saying earlier how the chloride, bromide, and iodide are strong nucleophiles, and the fluoride, is a weak nucleophile. Well, in reality, that depends on the solvent that I use. So if I'm doing an SN1 and I choose a protic solvent for the reasons we just discussed, a protic solvent really has, as we said, like water, for example, a really large partial positive on these hydrogens. And that can form a really strong attraction to the smaller halides. So, for example, the F minus has a really concentrated negative charge. It's a much smaller atom compared to like an I minus, a much bigger atom with its negative charge. The smaller the atom, the stronger these attractions will be. I've got a concentrated negative. It's going to form a really nice strong attraction with this partial positive. So if I have a protic solvent that can form a really strong attraction, that really hinders the fluoride's ability to act as a nucleophile. As we were saying, if the solvent forms a strong attraction to the nucleophile has a hard time reacting. It would have to shake off a bunch of solvent molecules around it. So I have a bunch of these solvent molecules around here. It would have to shake off that solvent shell to get free and to collide with an electrophile and push out a leaving group. So the smaller halides are less reactive in a protic solvent because it forms really nice attractions and prevents the halide from getting free to act as a nucleophile. So which would be the most reactive here? Iodide would be the most reactive, then bromide, then chloride, then fluoride, as we said, is relatively weak. If I'm working with an aprotic solvent, though, what actually happens experimentally, you can show the reverse occurs. In an aprotic solvent, we said, like for example acetone, the partial positive isn't really very large, and it's also not really very exposed. So I've got these methyl groups here, and they're blocking out the ability of that positive to form a decent attraction to the halide. And if the attraction here is not very strong, the halide is not blocked from reacting as a nucleophile. It can come in and attack a lot of different electrophiles. And so in that case, the fluoride is the strongest. Then the chloride, then the bromide, then the iodide. And that has to do with the stability of the charge, right? We know if there's 9 protons and 10 electrons, the charge ratio is unbalanced compared to iodine, where if you look on the periodic table, I'll grab my periodic table real quick. The iodine has 53 protons, and then 1 extra electron there. If I divide, the ratio is much closer to 1. So it's not nearly as a concentrated, unstable negative charge. So if it's not as unstable, it's not as strong of a nucleophile. It's not as likely to react. So naturally, the fluoride should be a better nucleophile. It should react more strongly because it's not as stable. it needs to share this extra electron with something to avoid this unstable charge balance. So in an aprotic solvent, the natural tendency of the charges to be either unstable or stable affect which nucleophile is more likely to react. But when the solvent is protic and it can really form strong attractions to these smaller ones, it stabilizes them more and makes them less likely to react. So you want to make sure that you can understand and explain that trend, as well as recognize when a nucleophile might be most likely to attack based on the solvent effects if the nucleophile is a halide. All right. So syntheses. This is a topic that we're going to see a lot more during the end of the semester and into OChem 2. But a lot of times you're trying to design the production of some molecule starting from commercially available materials, and so you want to pick out the right reaction conditions, the right solvent, all this stuff, and try to promote the specific mechanism that you're going to use to produce a product that you're interested in. So synthesis is all about choosing reactants, solvents, choosing molecules that have features like a good leaving group to facilitate a reaction that we want. So if I have a primary substrate, meaning my leaving group is attached to a primary carbon, I know it's probably going to be SN2. The only exception to that would be if the leaving group were to leave behind a carbocation that was stabilized by resonance. So if we assume there's no resonance to stabilize the carbocation that would form, I'm never going to form a primary carbocation. So in that case, I know it's going to be SN2. And so the nucleophile I would try to choose a strong one so that it would come in right away. I would try to choose a good leaving group so that when it leaves, it'll be stable, and that'll help facilitate that first step, the slow step of an SN2, which is the nucleophile attacking as the leaving group's leaving. And I would use a polar solvent that is aprotic, because I don't want the solvent to surround the nucleophile and prevent it from attacking. So this is mostly a summary of what we already said. We're just putting this in the context of the type of substrate that you might use. So what if I were working with a tertiary substrate? Well, if it's a tertiary substrate, I know I'll never have SN2. It's got to only be SN1, right? Because as we said, if the leaving group's attached to a tertiary carbon, it's too crowded for the nucleophile to come in right away. So the leaving group would have to leave first, then the nucleophile could attack carbocation. So here, I can use strong or weak. The nucleophile is not involved right away. It's not involved in the slow step, so it doesn't really matter whether it's a strong nucleophile or a weak nucleophile. I need for sure, as much as possible, to choose a very good leaving group here, because that's the slow step. The leaving group's leaving first. If I don't have a good leaving group, that first step's almost never going to happen, and I can't really get the rest of the process to happen either, because it's the slow step. And to facilitate the loss of the leaving group and stabilize the charges that result as it's leaving, I want to use a polar protic solvent. I want the solvent to have large partial positives to stabilize the partial negative that forms on the leaving group and help it leave. And that will facilitate the SN1 mechanism that I expect to occur on a tertiary substrate. If the substrate is secondary, well, it could go SN1 or SN2. Right? So if the leaving group's here on a secondary carbon, if it leaves first, well, that would produce a secondary carbocation, and that's not very stable, but not too unstable to form. Alternatively, since a secondary carbon is not super crowded, one of these bonds is to a hydrogen, it's not too crowded, I could imagine the nucleophile coming in right away and pushing the leaving group out. So I might also get an SN2. So depending on which one I want to promote, that's going to determine what I do here. I definitely need a good leaving group either way, because the loss of the leaving group is happening in the slow step in both mechanisms. So anytime I do a substitution, whatever type, I need a good leaving group. Depending on whether I want to promote an SN1 or an SN2, that would determine my choice of solvent and potentially also my choice of a nucleophile. So what are some good nucleophiles that I can use? Well, we were saying before, the stronger the nucleophile, or the nucleophile will be stronger when I have an unstable negative charge. So the sodium here is a counterion, right? It's just there to keep the charge overall balanced. My solvent would have a partial negative, and the partial negative would surround that sodium. And so the solvent would ideally carry that sodium away and expose the full negative on these nucleophiles, right? So the sodium isn't really part of the nucleophile. It really needs to be removed by the solvent to allow the nucleophile to be free and negative and attack and push out the leaving group. So whether this is primary, secondary, or tertiary, I want the negatively charged nucleophile to come in here and attack and push out the leaving group, maybe by SN1, maybe by SN2. But these are some common nucleophiles that you can use. As we said, oxygen with a negative, pretty good nucleophile. It can usually come in there and push out a leaving group. Sulfur is a great nucleophile. Carbon is an excellent nucleophile. And the CN, I mean, normally a carbon with a negative charge is really super unstable. On a CN minus, the negative charge on the carbon is not as unstable. So it's still unstable enough to act as a nucleophile and push out a leaving group, but it's stabilized by induction. Right? The nitrogen pulling electron density away because it's more electronegative than the carbon makes this carbon not so negative. I don't have nearly as much electron density around it if it's being pulled away by the nitrogen. So this is stabilized by induction enough that this molecule isn't like so reactive that it's dangerous or something to work with. I mean, it's poisonous, so it is dangerous to an extent, but it's stable in that I don't have to worry about exploding or eating through materials or anything like that. I can get the CN minus and use that to attack and then make a new structure that I might be interested in that has a CN group attached to it. So, depending on the structure and functional group I want to create for my product, I would select the correct nucleophile to come in and push out the leaving group and give me the product with the correct structure and atoms bonded the way I want them to be bonded if I were designing a synthesis. Alright, so here's the synthesis. So this was a quiz question for you to work through. The answers I looked at that you guys put up earlier were mostly great. What most of you realized was this is not a very good leaving group. Whether I'm doing an SN1 or an SN2, I need to make it a better leaving group. So I need an acid. I need this oxygen to pick up a proton from some base. So that if it picks up a proton and whatever the rest of this acid is, I think I said base, I meant to say acid. Whatever the rest of this acid is, it's going to hold those electrons behind in a stable way after the oxygen picks that up. And what I'm also noticing is the nucleophile I want to use is a Br minus because I want the Br minus to come in and replace this. So the good acid choice would be HBr. HBr is a strong acid. It's a very low pKa. It'll almost always react with any thing that can even remotely act as a base with a pair of electrons to pick up that proton. So the first step here would be adding HBr. The lone pair would pick up a proton, and that would make the OH into an H2, which is a much better leaving group. Right? Trying to get this to leave right away and produce a negative charge, not very likely. Now that I have a good leaving group, and at the same time I created my nucleophile because the oxygen picking that proton up off the HBr, the electron staying behind, gives me a Br minus, I could imagine this happening by SN1 or by SN2. If it were to happen by SN2, the bromine would come in right here as the leaving group. Is that possible? Sure, well, it's only a secondary carbon. It's not too crowded, and the bromine is just a single atom. It's not a massive grouping of atoms that's going to create a lot of steric hindrance as it comes in. So it could come in there and push out the leaving group. If that happened, though, that would only give me one product. Because if the leaving group has a solid wedge, the nucleophile, if it were happening by SN2, the nucleophile would have to come in from the back side, which would mean it would end up with a dashed wedge on the opposite side from where the leaving group left. So if I'm expecting to get both of these products, I'm anticipating at least some SN1 mechanism. So probably what most of you would have done would have been to wait, have the leaving group leave first, create a carbocation, and water would also be produced by the leaving group leaving, since it's water is the leaving group. Then the Br- could come in, and at this point, since there's an empty p orbital here, the Br- could come in from the bottom, giving me this product, or it could come in from the top, giving me the product with the bromine pointing up. And that would be an SN1. So HBr would work well here to facilitate both the OH being converted to a better leaving group and the nucleophilic attack at the carbocation that would result after the leaving group leaves. What about this one? Let's take a look at this reaction. So here I'm told I want to create this molecule from 2-chlorobutane. So if I draw a butane and put a chlorine on 2, I don't know whether it has a solid wedge or a dash wedge. I don't know if it's R or S, so I'll just draw it in there. So here I want the chlorine obviously to leave and be replaced. So if I number these carbons and then number these carbons, I can see that this group is meant to replace the chlorine on carbon 2. So I got to get the chlorine to leave, and I got to get this to end up attached with a solid wedge. Okay, so now I'm realizing if I want to create the product with a specific stereochemical outcome, I need the nucleophile to come in from the front to end up here with the solid wedge, which means the chlorine has to be kicked out the back. So the chlorine, so I would want to draw my main skeletal structure the same way. Put the chlorine here. If I start off with if I buy this molecule here, which is the R configuration, I would want to buy R2-chlorobutane. Then I could add my nucleophile. And since I want to promote an inversion of the stereochemistry here, where the nucleophile comes in from the top, pushing the chlorine out the bottom, I need to promote an SN2. The last example, I didn't really care too much if it was SN1 or SN2, but here I definitely need an SN2 because of the specific stereochemical arrangement of the product. If I want the nucleophile to be facing out at me, the leaving group has to be facing away, because if it's an SN2, the nucleophile will come in from the backside of where the leaving group is currently located. And if I want to promote an SN2, I need a strong nucleophile. So I would definitely add the nucleophile, and I would give it a full negative charge to make it as strong as possible. It would have to come with a counterion. I can't just buy ethoxide. I can buy sodium ethoxide or potassium methoxide or ethoxide, but I can't just buy this ethoxide molecule with the negative charge without a counterion. So I would also want to make sure I use a polar aprotic solvent so that the solvent surrounds the counterion. Maybe I'll use acetone. Like acetone, it's very easy to evaporate after the reaction. It's got a nice large partial negative that can, acetone molecules here can surround this counterion and keep it away from the nucleophile, but the partial positive is surrounded by these methyl groups, so it's kind of sterically hindered. It's hard for the positive to surround here, so my nucleophile should be fairly free and able to collide. And when that comes in and collides, it would have to come in from the front to push the chlorine out the back, and that should give me my product. So designing a synthesis is a little bit tricky. You have to select the right reactants and select the right solvent. I might want to think about the temperature necessary to facilitate the collisions. If there's some sterics here with these other groups, I might need a fairly high temperature to get to the transition state where this actually comes in and attacks due to the steric crowding that's occurring there. So there are other considerations as well, but those are the main points for that particular problem. Here's an example. Just wanted to point this one out where we're going to use a tosylate leaving group, and we'll see the reason for that. So far today, we've only seen one way of making a bad leaving group better, and that's to use an acid. So let's just imagine doing that here to see what would happen. So if I used H3O+, which we used in a number of examples today, as a way to protonate an OH through a proton transfer step first, that would make a great leaving group. That would make my poor leaving group into a great leaving group. Then it could leave, right, since it's a tertiary carbon, it could leave behind a tertiary carbocation. That would be relatively stable compared to primary or secondary. It's too crowded for any nucleophile to come in there right now anyway, so the only option is for it to leave. And then the nucleophile I want to bring in is a CN-. And so I could imagine that coming in and attacking here, and that would give me my product. So that all looks perfectly reasonable. The problem is that cyanide is poisonous. As long as it stays in a negative charge, though, it will remain in solution. As long as I don't drink it, I'm fine. When cyanide is exposed to an acid, it will pick up a proton, and that will produce hydrogen cyanide, which is a poisonous gas. And I don't want that, because then that's going to get me. And whether I drink it or not, if it's a gas, even with a fume hood on, I don't want to risk breathing any of that in. So I can't add an acid if the acid's going to react with my nucleophile, especially if it's going to create something that's dangerous for me to work with. So instead of that option, alternatively, there's another way to make this leaving group better. Instead of adding an acid to make it a water leaving group and give it a positive, which normally works, but in this case I can't use an acid because it'll react with the cyanide, I can use tosyl chloride and pyridine. So we're not going to get into the mechanism for this for a while, but basically the tosyl chloride looks like this. There's a ring here, bonded to a sulfur, and then I've got a chlorine here. So what's going to happen here, without getting into the mechanism, because it's more complicated than anything we've seen yet, we don't need to get into that level of detail yet. The pyridine, so this is tosyl chloride, and pyridine looks like this. Pyridine is a weak base. So what's going to happen here is this oxygen is going to connect to the sulfur, and the chloride is going to leave. And then this nitrogen afterward is going to pick off this proton. So all of that, in essence, when you see tosyl chloride and pyridine, what it's meant to do is to convert an OH into an OTS. And what that looks like is this. So I'm doing a substitution reaction here. I'm substituting the chlorine on this tosyl chloride. I'm substituting the chlorine for this molecule here, the rest of this structure. But the reason for that is it makes this a much better leaving group, right? So I can't push out the OH minus because the negative is unstable in that oxygen. But here, the leaving group can leave. Because here, if it leaves, it will produce the tertiary carbocation as well as the tosylate leaving group. tosylate leaving group, as we said earlier, is stabilized through resonance. The ring doesn't really do much. It's the SO double bonds that stabilizes negative over 3 oxygens instead of 1, and so that resonance really makes the negative quite stable. So it's much easier to push out a tosylate leaving group than an OH leaving group because of the negative being stabilized through resonance. And so then if I add NaCN, the Cn minus, and I would want to use a polar aprotic solvent like acetone. Well, actually, it wouldn't matter because it's an SN1 reaction. I'd probably actually want to use a polar aprotic solvent to stabilize the loss of the leaving group. So probably water would be reasonable. The water would help to stabilize the loss of the leaving group in this transition state of the slow step. And then the Cn minus would also be surrounded by water molecules, but since that's not involved in the slow step, that's okay. The Cn minus would come in here, and that would give me my product. So you want to try to find some practice problems that involve the tosyl chloride in this chapter if you can, because that's something that we'll see more in the future, and you want to get comfortable with that early if possible. And so then the last quiz question, this one's a little bit tricky because of the carbocation rearrangement, but these are my reactants. There's only 2 substances. The ethanol is relatively stable. It's a weak nucleophile. It doesn't have a negative. It doesn't need to react. Plus, I have a tertiary carbon where my leaving group's attached anyway, so I know that it can't come in here. It'd be too crowded no matter how strong the nucleophile was. So everything here is pointing to an SN1. The loss of the leaving group would have to happen first. That would create a carbocation. Anytime I create a carbocation, I want to look for a rearrangement, even if it's already tertiary. Resonance stabilized carbocations are more stable than tertiary ones that aren't stabilized by resonance. So I would do a hydride shift here to put the carbocation on a secondary carbon, because then it would be stabilized by resonance. It would be spread out over 2 different carbons, which is going to be more stable than having it on 1 carbon, even if that carbon is tertiary. Now that my carbocation is formed, and also ethanol is a polar aprotic solvent, so I would also use this as my solvent. It would help shift the equilibrium toward the product side since it's a reactant, and since it's polar aprotic, it would help to stabilize the partial charges that form here in the slow step where the leaving group's leaving. Once the carbocation is formed, the ethanol can attack. But now where's it going to attack? I've got 2 different sites that are electrophilic. Right? In reality, this structure has resonance. So there's equal, roughly, quantities of positive at both these carbons simultaneously. So in half of these molecules, the ethanol will attack 1 carbon, and in roughly the other half, it might attack the other carbon. So in some of these molecules, the ethanol will attack here. In other molecules, the ethanol will attack here. If the attack occurs here, that gives me 1 product. Down here. Oops. Oh, come on. Let me draw that over here. Hopefully it won't do that again. At this point, the ethanol is still protonated. I didn't really leave myself very much space, unfortunately. So another ethanol would have to deprotonate that, right? We said earlier, there might be a proton transfer step necessary at the end. If you're using a weak nucleophile and that nucleophile attacks and it becomes positive, you need something to pick up that proton to balance the charge. So that, in the end, would produce this as my product, or one of my products at least. after the deprotonation step. Over here where the ethanol attacks, this is going to create a chiral center. So you really also have to be careful about stereochemistry. If a new bond forms a chiral center at what used to be a carbocation, I have to remember that the nucleophile could come in from the top or from the bottom. So there's two products that will be created here. One where the ethanol would come in with the solid wedge, and the other where the ethanol would come in with the dashed wedge. But again, it's still protonated at this point. So the last step would involve an ethanol in each, for each one of these, an ethanol molecule would pick up this proton. And then over here, a different ethanol molecule would pick up this proton. And so I would get two more products that are only different spatially, but they're still different because they're not superimposable. They're a pair of enantiomers. Sloppy there. So I get a total of 3 products here from this reaction. So this is probably not a very good design for a synthesis. And if I'm trying to make one of these 3, I don't want my molecule to form a mixture of a bunch of different things, because then I have to separate some of them away from the others. Ideally, the best synthesis would create one structure and only one structure in a high yield. Any questions about any of that? All right, well, that's the end of chapter 7. There's lots more for you to practice. The more of that you can practice, the better you'll be prepared for next week's exam, or for those of you who have lab on Monday, the Monday following. Please let me know if you have questions or you'd like to set up an individual time to discuss some of these things. On Tuesday, we're going to get into chapter 8. It's going to cover the first 7 sections, although we won't cover the entire section of 7.8 or 8.7. We're going to start talking about elimination reactions, and there's going to be elimination mechanisms we're going to deal with. And that's it. So